All right, this is our lab notebook pages for lab 22. We are looking at moment of inertia from an energy standpoint. We're going to find the fractions that go before our mr squared for a solid cylinder, a hollow cylinder, and a solid sphere. Right, we already have these fractions, but we're going to see about the experimental values for these fractions. So our diagram is just some books and a ramp. We need the height of our ramp, and we also need the distance of our ramp. I originally put D, but then in my calculations I used X. So to make my equations line up with my diagram, I changed my diagram to read X. The materials are our ramp, the objects that we're rolling down the ramp, our stopwatch, the books for the height, and a meter stick. We're going to measure the height of the ramp, the time the objects go down the ramp, and we also need to measure the length of the ramp. And as I was going through my calculations, I realized we needed this, so we went back and added it there. So for our procedures, it's just very similar to other labs that we've done. My data table includes my time trials, and I took video analysis, so my start and stop times, the difference is the time it takes to go down. So these here are the actual times, and this is the average for each of the different objects that we rolled down the hill. The height here is from the center of mass to the lab table. So my sphere was just a marble, and so it was smaller in size. So the height of the marble is going to be smaller than the height of the other objects. So my solid cylinder was a can of tomato paste, and that was a little bit bigger than our sphere. And then the hollow cylinder is just a length of PVC, and that was a little bit bigger. So our heights are all different because our shapes are a bit different in size. All right, and then this, we decided it was X. All right, so these are the measurements for my calculations. Right, I started with conservation of energy. Right, these objects are rolling, so it starts with gravitational potential, ends with kinetic, both kinds of kinetic energy. Right, my R squared, W squared is equal to V squared. So I consolidated my equation, and also my M's end up canceling out. So this B is what I called our fraction, what we're looking for in the equation. You can call it X or question mark or whatever you'd like, but this is the value that we're solving for. So when I take out the M and do my conversion to V squared, take out the 1/2, multiply everything by 2. I factored out the V squared, and then I rearranged just for B. So when I did this, I was like, oh man, I need the velocity squared. Normally when we do this, we have one unknown, and it's normally the velocity that we're solving for. So I was like, oh, I got to go back and take a look at what else I need to collect. So in doing this, I was like, we can use the kinematic. We need our final velocity, but in doing that, we need some acceleration. We need to know our acceleration. So I solved for my acceleration first using the kinematic that we use most often, and then I took the value for acceleration and plugged it back into this kinematic. I have no initial velocity. So it's really my acceleration times time. When I plug that in here, right, acceleration times time, one of the t's cancels out, so it ends up giving me 2x over t. And I plug that in for my velocity squared. So I measured my height, I measured my distance along the ramp, I measured my time, And these are all things, so I'm doing one calculation for everything instead of finding my acceleration and then finding my velocity and then plugging it into the equation. I'm just doing this one equation. So I should get my unknown fraction when using the data from the data table. And I haven't done them yet, but we'll see how it goes.